You have learned the tools: acidizing, fracturing, stimulation design. But the real issue is this: why do the same tools produce completely different results in different systems? Because the system controls the outcome. Hydrogen is governed by containment. Carbon dioxide is governed by pressure and chemistry. Geothermal depends on circulation and heat transfer. Oil and gas focuses on flow optimization. The tools are the same. The physics is not. A decision that works in one system can fail in another. Aggressive stimulation increases production in oil and gas. The same approach destroys containment in hydrogen or carbon dioxide storage. So the starting point must change. You do not begin with the method. You begin with the system. Final principle: you are not applying a method. You are applying it within a system. Final line: same tools, different outcomes. Everything in this course depends on one model. Failure does not come from poor execution alone. It often comes from using the wrong system logic. The same method applied in the wrong system leads to failure. Each system is controlled by a different constraint. Hydrogen is controlled by containment. If there is any risk of leakage, you do not proceed. Carbon dioxide is controlled by pressure and chemistry. You manage pressure limits and monitor how the system evolves. Geothermal depends on circulation and heat transfer. Without flow, there is no energy. Oil and gas focuses on flow optimization. Aggressive stimulation is acceptable. Each system has one dominant constraint. Ignore it, and failure is built in. The process is simple. Identify the system. Identify the constraint. Then choose the method. Final principle: the objective defines the design. Final line: wrong system, wrong decision. System behavior comes from the objective. Hydrogen is built around containment. The fluid moves easily and escapes easily. So the system must be restricted. Carbon dioxide focuses on safe storage. Pressure builds, and chemistry changes the reservoir. So pressure and reactions must be controlled. Geothermal is about heat extraction. Fluid circulates through fractures. Heat transfers from rock to fluid. So flow must be maintained. Oil and gas is different. The objective is production. Flow is increased aggressively. These objectives define everything. Storage systems protect containment. Energy systems manage heat. Production systems maximize flow. Final principle: change the objective, and the correct decision changes. Stimulation does not improve every system. In some systems, it can destroy them. Hydrogen is limited by containment. Only minimal intervention is acceptable. You restore injectivity, nothing more. Carbon dioxide is limited by pressure and chemistry. You improve injectivity, but never exceed pressure limits. Geothermal is constrained by temperature and scaling. The system degrades, so intervention is required. Oil and gas is driven by economics. More stimulation increases production. Each system fails differently. Hydrogen fails by leakage. Carbon dioxide fails by pressure or chemistry. Geothermal fails by degradation. Oil and gas fails economically. Final principle: stimulation must match system tolerance. Not all systems can handle intensity. Risk is not the same in every system. Hydrogen carries the highest risk. Containment loss is permanent. Recovery is not possible. Carbon dioxide also carries high risk. Pressure and chemistry can create irreversible changes. Geothermal behaves differently. It does not fail once. It degrades over time. Oil and gas has the lowest systemic risk. Failures reduce production, but the system remains intact. The timescale also changes everything. Storage systems must survive for decades. Geothermal systems operate continuously for decades. Oil and gas works in shorter production cycles. The key difference is reversibility. Hydrogen and carbon dioxide failures are permanent. Geothermal declines gradually. Oil and gas failures can be recovered. Final principle: the longer the time horizon, the stricter the control. Consider one problem: low injectivity. Now look at 4 systems. Each has a different correct response. Hydrogen requires minimal intervention. You protect containment above all. Carbon dioxide requires diagnosis. You treat the problem, but always control pressure. Geothermal requires system enhancement. You may need to create or extend fractures to maintain circulation. Oil and gas allows aggressive action. You maximize flow and production. Same problem. Different solutions. The common mistake is applying one solution everywhere. That leads to failure. Tolerance for error changes across systems. Hydrogen has almost no tolerance. Carbon dioxide requires strict control. Geothermal adapts, but degrades. Oil and gas allows more flexibility. Final principle: the method is not the decision. The system is. Each system is defined by one objective. Hydrogen protects containment. Carbon dioxide stores safely. Geothermal extracts heat. Oil and gas produces flow. Fluid behavior defines risk. You do not control the fluid. You design around it. Stimulation intensity must match the system. Hydrogen requires minimal action. Carbon dioxide requires control. Geothermal requires engineering over time. Oil and gas allows maximum intensity. Storage systems have no tolerance for error. Small mistakes lead to failure. Geothermal systems must be maintained continuously. You do not fix them. You operate them. Final principle: identify the system, identify the constraint, then act. Look at all four systems together. Hydrogen demands containment. Minimal intervention. Highest risk. Carbon dioxide is controlled by pressure and chemistry. Intervention is limited and controlled. Geothermal depends on circulation and heat. The system changes over time and must be managed. Oil and gas focuses on flow. Aggressive stimulation increases output. Each system follows its own logic. Containment must be protected. Pressure must be limited. Reaction must be controlled. Time must be managed. Final line: different systems require different rules. This course was never about tools. It was about thinking. Most engineers repeat what they know. They maximize. They push. They apply the same approach everywhere. Sometimes it works. Sometimes it fails. And sometimes it destroys the system. A controlled engineer works differently. They start with the system. They identify what controls it. Containment, pressure, reaction, time. Then they act. Two engineers can have the same tools. Only one controls the outcome. The difference is not knowledge. It is discipline. Final principle: you are not applying a method. You are applying it within a system. Final line: understand the system, or lose it. You have completed the full system. You learned the foundations: acidizing, fracturing, design, failure, application. But this was never about tools. It was about control. You now understand flow. You understand pressure. You understand reaction. You understand time. That changes how you think. You do not react to wells. You control systems. You do not maximize blindly. You operate within limits. You do not assume methods. You match them to physics. A good engineer starts the same way every time. Identify the system. Identify the constraint. Then act. Final integration: design it right. Place it right. Operate it right. Store it right. Final line: control the system, and you control the outcome.